Okay, so let us get started. So, last time we saw the reduction, we saw the complete reduction as to why SAT is NP complete, and we also saw how SAT can be reduced to 3 SAT. So, let us look at one more NP complete problem. So, this is a this problem is related to graph theory, and we will show that the problem of checking whether the graph or whether an undirect or let us say directed graph has a Hamiltonian path or not is NP complete. Okay. So, how many of you here know what a Hamiltonian path is? Okay. So, let me just define it. So, let G be a directed graph okay. A Hamiltonian path in G is a path that visits every vertex exactly once. Okay. So, in other words, so when I say path in a directed graph, it means a directed path, and since it visits every vertex exactly once, what it means is that the length of the path is, if you count the number of edges, it is n minus 1, right. So, the language associated with this notion is, let us define the language as D Ham path. Okay. So, D Ham path consists of encodings of all graphs, all directed graphs G. Okay. So, for the purpose of this problem, whenever I am referring to graph, I will mean a directed graph such that G has a Hamiltonian path. Okay. Just D stands for the fact that G is a directed graph. I mean, I am just defining a language, D Ham path. So, it is just the name of this language. I mean, you can also define Hamiltonian path for undirected graph, and even there it is NP complete, but we will just look at the directed version for in this class. Okay. So, what we will show is SAT reduces to this problem. Okay. So, is this problem in NP first of all? How many of you think it is in NP? How many of you think it is not? Okay. So, why do you think it is in NP? Yes. So, you just guess a sequence of n vertices, okay, and now you check that does that sequence form a path or not. That can be checked in polynomial time. So, that is a polynomial length certificate and a polynomial time algorithm for verifying that D Ham path is in NP. So, therefore, this reduction would show that D Ham path is NP complete as well. So, I will give a sketch of the proof, I will skip some of the details that you can fill out later on. So, the idea of the construction is as follows. So, suppose you are given a formula phi, okay. We will construct a graph as follows. So, let us say that phi has n variables, okay, and m clauses. So, our graph will look as follows. So, for each of the m clauses, we will first add m vertices in this graph. So, let me draw a picture. So, we have some m vertices, okay, and for each of the n variables, we will have a chain of some n subgraphs. Okay. So, for each variable here, I will define a chain as follows. So, we have a chain 1 that corresponds to the first variable, then we have a chain 2, and what does each of these chains look like? So, they have a simple structure. So, each chain has 4 m vertices as follows. So, it looks like this. So, I take a vertex, I take a sequence of 4 m vertices, okay, and I add edges between them in this manner. So, I add an edge between vertex and its adjacent vertex in both directions. Okay. Maybe this is a vertex and this is a vertex. So, this is what each of these chains look like, and I have n such chains. Okay. Is it clear so far? Now, how do I connect these chains? So, what I do is that from the first and the last vertex of each chain, I connect the first and the last vertex of the next chain. Okay. So, from here I put an edge to the first vertex in chain 2 and to the last vertex in chain 2, and as well from the last vertex in chain 1 I put an edge to the last vertex in chain 2 and the first vertex in chain 2, okay, and so on. So, this is a chain. Similarly, I do this. All the way up to chain n. Okay. In addition, I add some more edges. Okay, so I add 2 more vertices as well. So, there is a start vertex. So, let me call it V start. And there is a end vertex, I will call it V end, and I connect the first vertex of chain 1 from V start as well as the last vertex, and the same thing I do for V end. Okay. So, now what role does these m vertices play? So, now I have basically defined the graph for these chains and their corresponding vertices. Now, what is the role of these m vertices up here? So, if a vertex, okay, or if a variable, okay, so suppose we have a variable use the suppose we have a variable x I in clause let us say C j, what I do is I add two edges from that particular from the vertex representing the jth clause to the chain representing the ith vertex. And how do I add it? So, let me illustrate it over here. So, suppose if I have this vertex representing the jth clause and I have a chain representing the ith vertex or sorry the ith variable, I take two adjacent vertices in this chain. Okay. Let us say I call them V I and let me not use I, let us use V I k and V I k plus 1 and I connect them as follows. So, if x I is present like this, then I put a connection from V I k to C j and from C j to V I k plus 1, and if x I is present in its negated form. Okay, so, if x I is present as x I naught, in clause C j, what we do is we just add these edges in the other direction. So, I add an edge from V I k plus 1 to C j and then from C j to V I k. So, now there is just one more thing about this construction that needs to be mentioned, and that is all. So, the question is that which of these two vertices do we pick? So, one property that I said these two vertices must have is they should be adjacent vertices, right. But what is this value of k that we are fixing? So, that value of k is some arbitrary value such that these two vertices are not part of some other clause. So, that is the reason why we choose 4m vertices. Okay. So, we have these 4m vertices sitting over here, right. So, these vertices must be spaced out in such a manner, so that there is always a gap of at least one such link between the edges going to let us say a clause j and some other clause j prime. Okay. So, maybe that there is also some other clause C j prime which uses the variable x I. So, I will just make sure that these two vertices are not used to connect C j prime, just some two other vertices, maybe something here and something here. Okay. For some other k prime. So, that is all. 2m is sufficient actually, yes, 2m is sufficient because a vertex cannot be part of more than m clauses, right. But then 4m is just to be safe, I mean just to make sure they are spaced out enough. I mean I think 2m is also sufficient, yeah, but basically just some constant which is sufficient enough, yeah. Okay. So, now what is the claim? The claim is that if phi were to be satisfiable, then there is a Hamiltonian path and otherwise not. Okay. So, let us check that. So, if phi is satisfiable, what can we say? That there is an assignment to the n variables of phi, right. So, there is some assignment, let us call it u1, u2, so on up to un, of values to the n variables of phi, which makes it satisfiable. Okay. So, what we do is we construct an Hamiltonian path corresponding to this satisfying assignment as follows. So, if a variable x I gets a value 0, we will think of traversing the chain from right to left for that variable, and if a variable gets a value 1, we will just think of traversing that chain from left to right. Okay. So, we start at V start. Okay. Suppose the chain 1 which corresponds to the first variable that gets a value 0. Okay. So, then what we do is that we traverse this chain 1 from right to left, we come to the head of chain 1, then we look at chain 2 and we see what value does it get. If it gets a value 1, we traverse it from left to right. If it gets a value 0, again we take this edge, come to the end of chain 2 and we traverse it from right to left. And we keep on doing this until and unless we reach the last chain, and we then go and stop at V end. Okay. So, basically this gives us a mechanism to traverse all the vertices from V start to V end and all the variables in the n chains, but we have not yet traversed these m vertices, right. So, Hamiltonian path must visit every vertex exactly once. So, the way we can visit these m vertices as well is because of the fact so, because of the way we defined these edges and the way we are traversing the chains. So, okay. So, if a variable got a value 0, then note that yeah, and if the literal x I complement got satisfied in some clause C j, then we have these two edges connecting C j to the ith chain. So, therefore, if C j got satisfied by the ith variable using these using a literal which has this form, we just traverse it from right to left, and when we reach V I k plus 1, I just take these two edges, come to V I k and then go ahead. Okay. And if a clause got satisfied by some literal which is in its non-negated form, okay, which has x I, then we know that the only way it could have got satisfied by x I is if x I got the value 1, and if x I got the value 1, I am traversing it from left to right. So, I can use a connection like this to go from V I k to V I k plus 1. Okay. So, instead of using this edge, I am just using these two edges, and the same thing is happening here. Instead of using this edge, I am using these two edges. So, the question is when a clause is getting satisfied, we just check which is the variable that is responsible for it and in which form. Is it getting satisfied by a variable in its non-negated form or in its negated form. Just to traverse, so suppose there is a variable which is not responsible for making a clause evaluate to 1, or basically for going from one end of the chain to the other end of the chain. So, that is where we use those links. If the ith variable is responsible for satisfying the clause C j, that is when we use that. So, it is not necessary. So, there can be many variables present in a clause, but we do not use all these jump edges corresponding to all those variables. We only use it for that particular variable or one particular variable which is responsible for setting that clause true. So, when we reach the first position, but see, one variable can be responsible for setting many clauses to true, but it can only have one particular value for that, let us say with a value 0 or a value 1. Okay. So, then we have many such jumps. So, we let us say it satisfies clause C j prime as well as C j. So, when I come to this vertex, I jump to C j prime, come back, or okay, in the other direction. So, when I come to C j, I jump to sorry, when I come to V I k, I jump to C j and then come back. again when I reach this vertex, I jump to C j prime and again come back, thereby satisfying both the clauses. And now, the converse is also not difficult to show. So, if this G has a Hamiltonian path, okay, what you need to observe is that any Hamiltonian path in G must start at V start and end at V end, because V start has in degree 0 and V end has out degree 0. Okay. And moreover, if you look at the way these chains are designed, you can only go from a chain I to a chain I plus 1. Okay. There is no other way in which you can visit the chains. So, any Hamiltonian path that you have, it must start at chain 1, then go to chain 2, chain 3, all the way up to chain n and then end. Okay. So, what you do is, if you take any Hamiltonian path and then in the middle of traversing this chain, there are some jumps to one of these vertices and down below. So, what can happen is, so there is only one problem case. Suppose you are at let us say some chain I, okay, and you make a jump to variable corresponding to some clause C j. Okay. So, there can be many variables contained in C j. So, let us say there is also another variable j. Okay. So, we have these two. Also, since there is another variable j present, I also have things like this, okay, maybe in the other direction. Okay. What if you go to C j using this edge, and then instead of taking the next edge and coming down to the ith chain, you take this edge and come down to the jth chain. Okay. What is the problem? Huh? So, suppose if you take this, go to C j and take this edge and come down here. Yes, then then just consider this vertex. So, let us call this vertex V. What happens to this vertex? So, there is no way in which you can your Hamiltonian path can visit V, because what are the outgoing edges out of V? So, there is one outgoing edge coming to this vertex and there is one outgoing edge coming to this vertex over here. Okay. So, and what are the incoming edges? So, there is only one incoming edges from one incoming edge from here and one incoming edge from here. Okay. So, the only way in which you can come back to V is by using this incoming edge, but then if you use this incoming edge, you cannot go to this vertex or you cannot go to this vertex, okay, because both those vertices have already been visited by your path. So, if you are climbing to some clause C j, you must climb back down to the same level or to the same chain I. Yes. Yeah. So, let me just draw this little more clearly. So, my claim is that if you are in some chain I, okay, and you climb to a clause, let us call it C, from some vertex u, okay. So, of course, you have some edge coming back here to a vertex V and you have edges like this. Okay. So, there is also another adjacent vertex sitting here, let us call this V prime. Okay. Now, there can also be another chain J which corresponds to some variable x j, which also belongs to C. Okay. So, yeah, I wish I had another colored chalk, but anyway. So, suppose after you come to U, so the Hamiltonian path that I am considering, after it visits U, it climbs to this clause C. So, it takes this dotted path, and then instead of climbing back down to the same chain, it climbs back down to the jth chain. Okay. What is the problem with this kind of a Hamiltonian path? The problem is that by definition the Hamiltonian path should visit every vertex exactly once. So, consider the point when this Hamiltonian path is coming to this vertex V. What are the ways in which the Hamiltonian path can come to V? Now, note that it cannot come to V from U, because U is already visited somewhere prior. The only way it can come to V is from V prime. Okay. So, this is the only way in which the Hamiltonian path can come to V, but if it comes to V from V prime, then it has nowhere else to go. Okay. In particular, it cannot reach, let us say, V end, because all the vertices that are connected to V have already been visited by that Hamiltonian path. So, it gets stuck. So, therefore, it always must climb back down to the same level. Well, we will not do that. So, basically what we do is, so I did not complete the entire proof. So, suppose there is a Hamiltonian path. Okay. So, of course, since it is a Hamiltonian path, it should not visit C again. By definition, it should visit every vertex exactly once. So, what I do is that, so now given a Hamiltonian path, I will define an assignment which is satisfying, assignment for phi as follows. So, if the Hamiltonian path traverses a chain from left to right, the ith chain, I will set x I is equal to 1, and if it traverses a chain, okay, so if this traverses from left to right, and if it traverses a chain from right to left, then I will set x I as 0, and my claim is that this is a satisfying assignment for phi. So, every clause will be visited by from some particular I. Okay. Maybe that many clauses are visited from a particular I, but there will be some I which will, from which there will be a jump to a clause and then back to the adjacent. Any other questions? So, what I suggest is you go back and complete this proof. Okay. So, the ideas are all present, just make sure you write down the complete proof, that will help you to verify the complete correctness. So, let us move on to a different concept. So, we will define this complexity class known as co-NP. Okay. So, what is co-NP? So, first let me define what it means to talk of the complement of a language. So, suppose you are given a language L, then L complement, what is the definition of L complement? So, sigma is 0 1 for us. So, it is 0 1 star minus L, all those strings which are not present in L. So, co-NP is defined as the set of all problems or the set of all languages whose complements are present in NP. Okay. If you want to be a little bit careful here, I can just say that set of all languages L such that L complement is in NP. Both way of writing it is correct. So, a couple of points regarding this definition. So, the first thing is that, so note that co-NP is not the complement of NP. So, sometimes this term co can be a little bit misleading, okay, and so that is why I just wanted to emphasize this. Co-NP is not the complement of NP, and as it turns out, the intersection of NP and co-NP is not even is not empty as well. It contains a rich collection of classes. In particular, it contains the class P. So, we know that P is contained in NP. You can also show that P is contained in co-NP as well. So, this is, you can try this as an exercise to show that NP intersect co-NP contains P. So, the second point is so let us consider the complement of the language SAT. So, what is the complement of SAT? It is the set of all formulas phi such that phi is unsatisfiable. So, is this the correct complement of this language? Why not? Who said no? So, what was SAT? What was the definition of SAT? There exists, so it is all formulas phi, let us say in CNF form, such that there is some satisfying assignment. And now, here I claim that it is SAT complement or SAT bar is the collection of all those formulas which do not have any satisfying assignment. So, unsatisfiable basically means that there is no satisfying assignment. So, is this the correct complement? So, let us look at the definition. The way I define the complement of a language here, that is the point. So, I am so when I wrote down this definition, I was a little bit lazy and I kind of abused the notation that I defined earlier. What if you have a string which does not encodes a formula? What about those strings? So, by definition SAT is encodings of all those strings which are satisfying formulas, right. So, therefore, SAT bar should not only comprise of all these kind of formulas, but also those strings which are not let us say formulas in CNF form or some arbitrary string. Okay. So, generally, so this is a point that I want to make at the beginning of this course. So, generally when we look at complement of languages, we are kind of abusing this notation and we only look at those strings, okay, which represent an instantiation of that problem, okay, a correct instantiation of that problem, which gives an alternate answer. So, in the earlier case all those formulas which belong to SAT, they had a satisfying assignment, and here I am considering formulas which do not have any satisfying assignment. And the reason why I can do that is because if you are given some other string, I can easily check that. I mean, I can easily run through the string and I can check whether it is a valid encoding of a formula or not, and depending on that I can just accept or reject. Okay. So, that is the reason why I can make such a definition. Okay. So, just keep this point in mind. Okay, yeah. So, coming back to this language. So, now consider the following potential NP algorithm for SAT bar. So, we know that SAT is in NP. Let us try to prove that, or let us try to see if we can come up with an NP algorithm for SAT bar as well. So, potential NP algorithm for SAT bar. Okay. So, what we do is, given a formula phi, guess a an satisfying assignment x of phi. Okay. So, you just make a construct a string x comprising of assignments to the variables of phi, and if now plug in those values onto phi, and then if phi of x is satisfiable, then reject, okay, else accept. So, this algorithm is clearly guessing a string which has polynomial length, okay, and this string is satisfiable or not, that can also be carried out in polynomial time. So, is this a correct algorithm for this language SAT bar? So, therefore, this is an incorrect algorithm. So, this is again a common mistake that people tend to make. So, that is why I wanted to point this out. So, when we say that a language is in co-NP, what it means is that for all possible certificates, okay, so not only for one certificate, for all possible certificate there is a polynomial time Turing machine which does which accepts or rejects, however way you want to define it. So, let me just write that. So, we say that a language L is in co-NP if there exists a polynomial P and a polynomial time deterministic Turing machine M such that for all x if x is in L, I mean x is in L if and only if for all possible certificates u of length p of x, m given x comma u would accept. So, you can verify that these two definitions are the same. So, therefore, to show that a particular formula is unsatisfiable, you need to basically check for all assignments x whether m on x comma u satisfies or not. Okay. So, it does not suffice to check it just for one particular assignment. So, this kind of motivates why this question is so interesting. So, this is also an open problem. Whether NP is equal to co-NP or not. Okay. So, basically resolving this question amounts to coming up with a polynomial length certificate for SAT bar. Okay. So, can I come up with one particular certificate which is able to verify that a formula is unsatisfiable. And that kind of if you just think about it for a while, you will realize why it is so difficult, because there are exponentially many possible formulas, and it is not easy to come up with such a logic. In fact, it is believed that it is the other way around. So, the general belief is that these two classes are probably not the same. Okay. So, let me define some more things and then we will stop. So, we can define exponential time classes in a similar manner. So, EXP is the class of all languages which are the union of the languages contained in D time 2 to the power n to the power c. Okay. So, recall that polynomial time, the class P was defined as the union of all the languages which are the union of D time n to the power c. So, here we have this exponential term, and similarly NEXP is union of all languages in n time 2 to the power n to the power c. Okay. So, what do we know? What are the known relations between these classes? So, by definition we know that P is contained in NP, okay. And again by the definition of EXP and NEXP, we know that EXP is contained in NEXP as well. Also from the definition we know that P is contained in EXP as well. Okay. So, we can give an EXP algorithm for SAT as follows: just run through all possible strings of length n. Okay. Suppose it says SAT on it is a formula on n variables. So, just run through all possible assignment of values to those n variables. Okay. There are 2 to the power n many of them, and keep checking. So, if you find even one such string which makes the formula satisfiable, then accept, otherwise reject. Okay. So, that is a deterministic algorithm in exponential time, which shows that NP is contained in EXP as well. Okay. So, we will stop here today. Next time we will see a little bit more about these classes.